Awesome. Thank you, Rachel. Well, it is my absolute pleasure to introduce Allie Goldman, or Allison M. Goldman, which will be the name that is next to mine, Allison M. Fleshman, on the paper that we are writing from the work that she is doing right now, which I am so proud. So I've known Allie for several years, and she's been such a phenomenal student in the chemistry classes that I've taught. But also, I want to take a moment to acknowledge her for just being her. She has been crucial in me getting through the rut that is the pandemic. I hadn't touched my research in about a year because of maternity leave and all of that. And then Allie came to me and she said, well, so how is senior experience going to work now that we're remote? And I kind of threw this idea about, well, what she's going to talk about today. And I was like, well, what do you think? And she was like, absolutely, this sounds great. And she took it so much farther than I could have ever imagined. Not only that, in the questioning and her practicing science before my eyes inspired me to dive in with her into the literature. And I have now spent so much time working on this paper because of her excitement and dedication and what she's found and what she's going to share with you now. So I kind of have this second wind in my career, and it really is. Thank you, Allie. You have been so great and helpful in this, and I am so pleased to I'm excited that we get to have our names as co-scientists together on this paper. I should also add that she's going on into law school after this. And so we are not sad to see her go from science because we know that she's going to take the science with her because she'll forever be a scientist in my heart and in my mind because you are just a rock star overall. And you're a badass trumpet player too. So, or trombone. I totally messed that one up. I'm so sorry. I had the picture in my head and it said trumpet instead of trombone. Anyway, that's all I got to say. Allie, you're amazing. And so I look forward to hearing your talk.
All right, let me share my screen. Okay, can everybody see okay?
Yes, we are good.
Well, for starters, thank you so much, Allison, for that really beautiful introduction. And thank you to everyone who's come here today to hear about my capstone project. Today, I'll be talking about my research on how ions interact in ionic liquids. So my capstone project is a little bit unusual because I had this opportunity to work with Allison, who was sitting on a bunch of data but had never published it. Because of these kind of changing scientific discourses, it was really important to update the interpretations of the data in the context of newer work. So I've come in and have had to understand this existing data kind of as if it were my own, even though I wasn't in the lab measuring it, and contextualize it so that we can write this paper for it. So before I get into some of the work that I've done on the project, I want to talk about a little bit of what I'm building on, which is this work with the CAF, or the compensated Arrhenius formalism. This equation has 3 separate parts, which I'll break up for you before putting it all back together. So this first part of the CAF, the one in pink, on the left is f of t, which says in short that the fluidity is dependent on temperature in some way that the right side of the equation is going to be telling us. So even though you might not be super familiar with the term fluidity, you're probably familiar with its inverse, which is viscosity. So I'll be using that instead of fluidity in the presentation, since it's probably a little bit more intuitive for most people listening. If you aren't familiar with viscosity, picture some honey and some water having a race. You probably intuitively know that the water would move a lot faster than the honey, but viscosity is a reason why. So the honey has a much higher viscosity, which in this kind of chemistry sense is a measure of how much the molecules in a liquid want to hold on to each other and how high the energetic barriers are between them and being able to move. Moving on with the CAF, we have this next purple section, which is the pre-exponential factor. This part of the equation uses the solvent dielectric constant, that epsilon sub s that you see, to describe the temperature dependence of fluidity. The dielectric constant can be thought of as a measure of polarity, so the higher it is for a solvent, the more intermolecular attraction there will be. By incorporating this into the prefactor, the equation describes how intermolecular attraction plays into transport and describes that as temperature dependent. So our last part of the CAF is this part in blue, which is the Arrhenius component, which should look a little bit familiar if you've taken PChem. This part of the equation describes transport as having activation energy barriers which need to be overcome for the molecules to move. So it's not able to move until it overcomes that activation energy, and then it's able to move. So to bring all of these things together, the compensated Arrhenius formalism is an equation which describes molecular transport, in this case fluidity, as having a thermally dependent component dependent on intermolecular interactions, and also having an energy of activation. The really cool thing about this particular equation is that everything in it relates back to the system and its specific properties. There aren't any fitting parameters that don't have any chemical meaning. Everything in it relates to what's actually happening at the molecular level. So coming into this project, like I mentioned, Allison was sitting on a ton of data, which was using this compensated Arrhenius formalism to look at ionic liquids. But there were missing pieces when it came to interpreting that data in the context of ongoing discourses surrounding ionic liquids. The challenge is science changes really quickly. So while talking about this whole thing to Allison, she mentioned the term publish or perish, which I'm sure many of you are familiar with. But I think the way that we typically think of that term is in terms of academic institutions. If you don't publish, then academic institutions won't want you on their faculty or things like that. So we often think about it in those terms, but Allison mentioned this as a sort of different publish or perish, where unless you publish your research, the discourse that surrounds it is going to change, and you're going to need to update that existing data to match those discourses. So the challenge of this project has been taking that existing data and those existing interpretations that we had and situating it in these discussions that have changed a lot since the data was first taken. So to get into what ionic liquids are, because I've been throwing that term out a whole lot already, I'll introduce a relationship that you might be a little bit more familiar with, which is the fact that all squares are rectangles, but not all rectangles are squares. Applying that to ionic liquids, all ionic liquids are salts, compounds that are made up of these positive and negative ions, but not all salts are ionic liquids. So for example, sodium chloride table salt is not an ionic liquid. So what makes it not an ionic liquid is that ionic liquids are differentiated from ordinary salts in that they're liquid at room temperature, hence the name liquid. They're often made up of organic or inorganic molecules, and they have tunable macroscopic properties like viscosity, which I mentioned earlier, based on their overall structure. This is because when you have these organic or inorganic molecules, you can change them and change their functional groups or alkyl chain length or things like that. And that has an impact on the way that the molecules interact with one another, which then transitions to applying to the system as a whole. So before moving on to our specific research, I think that it's also really important to discuss what makes ionic liquids an important area of research in the first place. Right now, ionic liquids are being used for a huge range of practical applications. To name just a few, they've been used as less toxic solvents, batteries and fuel cells, and they've been used for drug delivery. This makes them a really important area of research for everything from green technologies to medicine. On top of these kind of obvious practical applications of ionic liquids, there are also some really novel and unexpected uses for them. In the picture here, you can see the Finnish First Lady wearing a dress made from birch tree fibers at Finland's Independence Day in 2018. In order to create this dress, ionic liquids were actually used to isolate these fibers, which were made into the fabric. And the dress was seen as bringing a lot of awareness to environmental issues and the need for renewable resources, which is a political statement that I certainly didn't expect ionic liquids to be making. So for these actual applications of ionic liquids, the research fits in a really important way. You have your potential solution. As an example here, we'll use using ionic liquids as a green solvent. And in order to get to the implementation and change, you need to have the research to back up the viability of that potential solution. In this case, getting labs and industries to transition to ionic liquids might need the research step of finding an ionic liquid which will work for a particular application. So this research step is broken up into a lot of different aspects. To find an ionic liquid which works for the particular research or industrial applications, researchers would need to make sure it doesn't interfere with the reaction mechanism. They would need to make sure it isn't unreasonably expensive. They would need to make sure it's safe to manufacture and answer a ton of really similar questions. The part where this work comes in is this last one, making sure that the ionic liquid isn't too viscous to be easily used for a particular application. So even though this work might seem really zoomed in since we're looking at these individual intermolecular interactions, it has these big applications which tie into what's going on with ionic liquids in general and to these specific practical applications. So let's get into a bit of what that research is and what it looks like. As an example, when the alkyl chain length is lengthened on some cations in ionic liquids, it results in a decrease in viscosity due to a decrease in the Coulombic intermolecular attraction. Essentially, the lengthening of the alkyl chain pushes the molecules further apart, which makes the positive and negative ions attract one another a little bit less. The problem with this is that it's not a hard and fast rule that we can take and apply to every single ionic liquid. This one structural change has a lot of impacts on the intermolecular interactions that we need to consider. So it adds steric bulk, which could reduce the viscosity, but it also results in more attractive London dispersion forces between these chains, something which could increase the viscosity. And like I mentioned before, it could also reduce the Coulombic interaction, which would reduce the viscosity. So as you can see here, one small change ends up having a lot of different potential impacts. And we need to start considering how these things look in the big picture. So as you can see, understanding these individual impacts of the interactions isn't enough to get this big picture of how functionalization affects transport. And then on top of this, the types of interactions which we've been considering have changed a lot over the course of the project. When I came into the project, we were looking at things like the impact of functionalization on sterics, Coulombic interactions, and the weak hydrogen bonding that occurs between cations and anions in ionic liquids. But as we've continued to dig into the current discourse, more interactions have popped up that we need to consider, like pi-pi stacking, conformational flexibility, and ion basicity. So suddenly, instead of considering just a few potential impacts that functionalization could have, we need to consider a lot more and how their potentially competing effects might impact the net effect on molecular transport. So to get into our specific system in this work, we used imidazolium cations and a couple of different anions in the ionic liquids. With the imidazolium cation, we had different chain lengths, which changed viscosity in a way that was consistent with previous work. And then we also had this methylation of the C2 position, which acted as a sort of on-off switch for hydrogen bonding. When the cation is methylated, it isn't able to hydrogen bond with the anions, but when it's left as is, it can hydrogen bond with them. So getting into the specific anions, we had the NTF2 anion, which can hydrogen bond with those imidazolium cations, and the BCN4 minus anion, which can't hydrogen bond with them. So you have this sort of on-off switch with the imidazolium, and that's only acting as an on-off switch with the NTF2 minus anion. With the BCN4 is kind of like a control. It doesn't get impacted by that change in the hydrogen bonding as NTF2 is. So we had a little bit of a mystery in the data, which is that we had the red, the imidazolium cation methylated at the C2 position, and the blue on these graphs, the non-methylated imidazolium cation. And with the NTF2, which experiences hydrogen bonding, this methylation and removal of the hydrogen bonds results in an increase in the overall viscosity. Which, to clarify why that's so weird, we see that less intermolecular attraction, or what we would think would be less intermolecular attraction when there are these hydrogen bonds not there when it's methylated, is resulting in an increase in viscosity. So when you would think that these ions would be holding on to each other more tightly, they're actually not. And when you would think that they would not be holding on to each other quite as much, they actually are. So we needed to look and see what answers we could find for why this was happening. So I started off my research with looking at a paper by Patricia Hunt, which talks about an idea of stable conformers. And if you think about it, there are certain spots that ions can be in where they're more comfortable, where they're more stable. So what Hunt looked at is the relationship between those number of stable conformers and the entropy and thus the viscosity. So by studying these individual ion pairs, it's a computational study. So basically just making calculations based on the positive and negative ion. She found that more stable conformers means more entropy and a lower viscosity. So the more of these are, the more states they can exist in, leading to that higher entropy and decreasing the viscosity. So the problem with this theory is that, yes, it explains what's happening, but it doesn't give us the answers for why. So we have this existing data, which already tells us what's happening. There's this unexpected trend, but we're looking for an answer for why that trend is there, not more information about that trend. So as good as this was to consider, it also wasn't the answer that we were looking for. From there, I moved on to the work by the Femino group, which talked about hydrogen bonding as something which is highly directional, short range, and strong. By comparison, Femino describes the Coulombic interactions as something which created more of an ion network that was a bigger structure, it was longer range, and it was weaker. So Femino's group essentially said that this strong directional hydrogen bonding disrupted the greater ionic network and resulted in a lower viscosity. And the problem with that is that it doesn't acknowledge how many different interactions are at play. They assume that hydrogen bonding is universally destabilizing, but they don't really consider that it might just be one interaction in a big scheme of different ones. And I pulled this quote on the left just because I thought it was really funny that Femino's group essentially wrote off everything that Hunt had said because she made the assumption that in certain circumstances, hydrogen bonding could be stabilizing, which we find that it is. So then we have the Filippi paper that I looked at, which talked about conformational flexibility of ions. In this, Filippi talks about the relationship between low energy conformations, like the ones that Hunt looked at. So instead of considering, like Hunt did, the number of low energy conformations, Filippi was looking at the barriers that exist between them. So if an anion is conformationally flexible, it has really low barriers between stable conformations, which allows it to move more easily between them. So Filippi's group found that conformational flexibility augmented the effects on transport properties from other functional groups. So if you had a conformationally flexible ion, and you increased the alkyl chain length, like I mentioned earlier, that increase in alkyl chain length would decrease the viscosity. But if you have conformational flexibility thrown in there, it would decrease it more. So this alone wasn't an answer, because if you think about it, that tells us about the magnitude of change, but not the direction of change. And what we're looking for answer-wise is something about the direction of change. We have something that isn't going in the direction we expected it to. But the thing that was really useful about this paper was that it was a tip to try focusing on these specific ions. So in this paper, they discussed how the NTF2- anion is flexible and the BCN4- anion is rigid. And this distinction between them is something that we hadn't considered or tried looking at. So we started looking more at zooming in on these specific ions and what they're bringing to the table. And that brings us to the Matthews group, which talked about how the imidazolium cations interact with one another. So in the Matthews paper, they discussed how pi stacking occurs between imidazolium rings in an ionic liquid. So this example uses a chlorine anion, which we didn't, but those interactions still occur between the rings. But essentially, the rings interact with one another and stabilize it through these pi-pi interactions. And the Matthews paper also talked about how the NTF2- anion specifically interrupts these interactions. So when the NTF2- anion is able to hydrogen bond with those imidazolium cations, it forces those imidazolium rings further apart and prevents that pi-pi stacking. So tying this into our work, we had hydrogen bonding between the NTF2- the anion and the cation, that imidazolium cation. And this interrupted stacking described in the Matthews paper is one explanation for that lower viscosity that we see. So when the hydrogen bonding occurs, the rings are forced further apart, decreasing the viscosity. As a comparison to that, we have the BCN4- anion, which in the Matthews paper is described as always interrupting this stacking. So that's one more way that this anion is acting as a control. So not only does it not have that hydrogen bonding on-off switch as we're methylating the imidazolium cation, but it also always interrupts the stacking, so we don't need to consider that in the same ways. And there's this negligible change in viscosity, which makes sense because effectively, this is just a small structural change through methylation. So where we're at now, we found this new research and updated our approach to the paper. Suddenly we have this pi-pi stacking thing to consider, and it explains a lot of what we're seeing. Even though we don't have all of the data to say for sure that that's exactly what's happening, it's something that we can throw out there to support what data we're seeing. Right now, we're working on writing the paper and incorporating all of these new ideas. And then next, we'll be sharing it with other authors on the paper and moving on to publishing. So as far as goals for the paper go, one of the really important aspects of the paper is that it applies the compensated Arrhenius formalism, which I introduced at the beginning. And even though the CAF is the only way of looking at molecular transport in this kind of way, using system-specific properties, it hasn't really been accepted and used by the scientific community as a whole. So by getting one more paper out there that can show how this can represent really complicated systems, like ionic liquids, where we're juggling these Coulombic interactions and all of these specific intermolecular interactions, and showing that this model can accurately represent that, we're giving it a little bit more traction, which hopefully means that other people will be willing to use it as a tool to look at the work that they're doing. One of the biggest things that I learned through doing this research is that the science doesn't only happen in the lab. I know that this is something that I really struggled with, where I thought that I wasn't doing science unless I was the person measuring data or making graphs in Excel. And I learned a lot about what science is. I think I've come to see myself as so much more of a scientist through doing this work, which is something that I didn't expect through this process of researching and writing a paper. This has probably been my experience at Lawrence, which has most made me feel like a scientist, even though I didn't spend a single minute in a lab on this project. When I came into it, I didn't think that I would be worthy of saying I was an author on this paper, but now I can absolutely say that through finding these connections in the data and creating this, that I am an author. So to wrap things up, I want to say a huge thank you to all of the scientists who helped synthesize the ionic liquids and collect and interpret the data before me. So we have Stefan Debert, who synthesized them, Wesley Hetcher, who came before me and gave me his notes to look at going into this project, Allison, of course, and then her colleagues at Oak Ridge, Shannon Mahurin, and Chilin Dothan. And then I also want to say a huge thank you to all of the people that have helped me along the way. All of the chemistry faculty at Lawrence, I am so unbelievably thankful. The trombone studio, which a few of them are here today, and I'm so unbelievably grateful for them coming to hear me talk about this. And then my two academic advisors, Tim Albright, my trombone professor, who has been there for me every single step along the way, and Allison, who absolutely I can say the same about. And especially Allison, thank you so much for including me on this project. It's meant so much to me to be a part of this, and I'm so unbelievably grateful for that.
Yay! Go team. Thank you, Allie. That was awesome. Oh my gosh, that was awesome. Cool. Well, you have the floor for any questions that anyone might have.
Can I ask a question? So Allie, I'm curious, and I'm not sure if you're at this point in the paper yet, but it's exciting to see you kind of solve the mystery and see what the interaction is. And maybe this is something I just missed, but how do you parameterize the information that you found, namely this pi stacking effect, into something that you can build into your model? What is kind of that key physical parameter that you're building into the mathematical model?
So I think a lot of this, Allison, correct me if I'm wrong, but the differences that we're seeing in the prefactor with, the prefactor is the section of the equation that talks about how these intermolecular interactions impact things. So with the prefactor, we would see that even though we're expecting less intermolecular interactions with the removal of hydrogen bonding, we're actually seeing an increase. Even though that doesn't specifically tell us this is absolutely pi-pi stacking, it's the thing that makes sense. So That's why it's not a for sure, this is absolutely 100% what's happening, but that's where you can see it in the data.
Perfect. Awesome. And
Yeah.
I just wanted to, oh, sorry, Allison.
I was just going to add on to that. One of the challenges is that so all of this work that Allie's shown, there's also a temperature dependent component, which they don't necessarily have data out there for temperature dependent component. Allie spent a lot of time looking at computational results, which can't be trusted at various temperatures. And so that's just an added layer of challenge of trying to interpret what these temperature dependent data are showing. And the kicker is that within the pi-pi stacking, as well as the Coulombic interactions, they each have a different type of temperature dependence. And so the prefactor can kind of help elucidate the various types of dependencies. And so that just adds an additional challenge that Allie didn't even touch on. So this interpretation, it goes much deeper than even she showed. And so she's been able to help kind of clarify those things, but it's all in the prefactor, and figuring out that prefactor has been such a challenge.
It's very exciting. So I just also wanted to say thank you for your comments about being in the lab versus, doing the work that you did. And that's just a wonderful lesson, I think, for all of us. So, thanks, Allie.
I have a question. So why do you think that the or like a better way of explaining it than some of the previous theories that you talked about?
So, sorry, you were breaking up a little. Do you mean why is the compensated Arrhenius formalism better than alternatives?
More why the pi stacking, like most recent paper, why is that idea more accepted or maybe quote unquote better than the other theories that you talked about?
Yeah, so if you think about it, that's kind of interacting with the Femino theory, which is, the Femino theory is this idea that the directional strong hydrogen bonding is interrupting other interactions. Though they said that it was interrupting the Coulombic interactions, which could be true, but the pi-pi stacking occurs like on a similar amount of energy as those hydrogen bonds. So as far as energetics go, it makes sense that it's that. And then it's also, it can be thought of as kind of adding on to that Femino idea of the hydrogen bonds interrupting things.
Cool. Thanks.
I guess I was wondering, it seemed like a lot of this project for you was almost like a detective game or something where you're trying to solve a mystery. So I was wondering how you worked through these different papers and put them into a discourse with each other.
Yeah, it really was. That's completely correct. It was absolutely a mystery, and I was trying to kind of investigate and figure out where the answers were. I think as far as like actual research process, it wasn't quite as linear as it seems in a presentation. There were certainly weeks that I came in and I was like, Allison, I have nothing. I don't know what's going on. But I think the more time I spent with the research in general, the better a picture I had of what the discourse surrounding ionic liquids was. So it was a little bit more difficult situating things in the context of other things at the beginning. But the longer I went, the more I was like, wait, this complicates this idea in this other paper, and kind of naturally started tying things in. I also kept an insane document that had notes from every single paper and connections between them and things like that. So I think taking notes as I was going along the way was definitely a huge part of making those connections as well.
I was particularly struck by that one quote where the author called like the hydrogen bonding, like the so-called hydrogen bonding. And I was just kind of wondering, like, is there a lot of pushback to like this further research into how ionic liquids work? And do you maybe expect that there'll be pushback against the paper that you're going to publish eventually? Kind of a broad question, but yeah.
Yeah, no, that's a wonderful question. There's a lot of pushback against computational work in general that I noticed, especially because Hunt's looking at these individual ion pairs and doing computational work with an ionic liquid. You have, this infinite number of ions that are interacting with one another, and not all of those interactions can be represented by looking at one single pair of them. So I think that's part of where that distrust of Hunt's work came in. But I think in general, I know Allison can probably elaborate on this, but I know there's a lot of mistrust for the compensated Arrhenius formalism in particular, because it doesn't match up with things that people learned as they were going through PChem. So because they don't have that kind of firsthand experience of seeing that it works, I think there's a little bit of mistrust coming from there, but I'm sure Allison can expand a lot on that kind of stuff.
You said it well, but I think it's one of the beauties of Allie diving into the literature as she did, is you get to know the people, and you kind of get to know like the groups that you can kind of quickly recall, like, oh, well, that's the Femina group. Well, that's definitely Hunt. That's Hunt's influence over here. And you really do start to see the dialogue, because the scientific literature really is a dialogue of, hey, this is what I found. We're at the forefront, or that boundary of our understanding, and we're trying to push it forward. But only maybe 1 out of 1,000 that push it forward actually push it forward with getting it right. But what is right? And so there's going to be a lot of kind of this gray area of, well, we think this, we speculate this, it could be this. And sometimes people do take it a little personally, where I've seen them, outright say that, well, they are misinformed, or their data might not actually show what they say it shows. But it is a discourse, as Allie has emphasized this entire time, is that there is a conversation going on between the reader and the producer of the science, and we won't get it right. That's the kicker, and it's hard to convey that to students until you kind of really start to swim in the literature. But we can only do so well with the models that we have, and we have to just continue to critique and question those models. And this is just a way that Allie's at least helped me continue to critique this model that may or may not be right. I think it is. But then again, that also has its internal bias associated with it. So until the data show me otherwise, I'm going to keep pushing forward with my students, hopefully.
Gotcha. Thanks, Allie, and congrats.
Thank you.
I have one for you, Allie. And by the way, I hope you publish the formula in pink and purple as you did in your slide. That would be an excellent addition to the black and white literature. So you mentioned sort of the unreliability of computational work, and I've experienced that as well. Do you think that your work with this formula, pushing the knowledge boundary forward just a little bit, will that improve the accuracy of computational work in your subfield?
I think so, because one of the things that differentiates the compensated Arrhenius formalism from other work that kind of tries to represent transport properties in general is that it is all tying back to the system-specific properties. So it both is and isn't computational. It's not in the sense that it ties everything back into what's actually happening and tries to root it in these kind of baseline chemical principles. So I think that it's kind of making that bridge happen between what's happening and the more computational work.
I hope so.
Your team, any other questions for our speaker?
I have one quick one for you, Allie. You had mainly the 2 compounds that you were looking at, and that we saw in your presentation, and I was wondering if those 2 were the only ones you looked at, or if you looked at other molecules as well.
Yeah, so the data, I kind of simplified things for the presentation, but like I mentioned, there was the methylated or non-methylated, and then there was also alkyl chain length. So I forgot how long out the alkyl chain lengths went. I want to say it was like 8 or 10 carbons. I at maximum, and then I think just like 1 at minimum. So there was like a huge range of compounds because you're looking at all of those different alkyl lengths and then also the methylated or non-methylated. But the only anions were those 2 that I mentioned. So it's basically all this huge swath of the imidazolium cations with different lengths and different, methylated or non-methylated, and then the corresponding anions.
Cool, thank you, and congratulations. It was a great presentation.
Thank you.
Go team. Well, if you are that much more curious about the work, please look towards the Journal of Molecular Liquids probably in about 4 months. Hopefully you might see this in press. We're very excited. And Allie, thank you again. You've been phenomenal to work with. So yay, go team.
Thank you.
All right, I believe we have another talk tomorrow. Is that Wednesday? Is that correct? Stevens is next at 4 o'clock tomorrow. So I hope to see all of you there.